Hello, I'm Giulio Alessandrini. I'm the manager of machine learning at Wolfram, and today I'm going to talk about semantic search and RAG, both in general and in practice, how to do that within the Wolfram language. Let's have a look at the topics that we're going to cover in this presentation. I'm going to start pretty broadly, talking about what is semantic search and how it relates with traditional search, how it overcomes part of the limitations of traditional search. And also maybe what are the limitations of semantic search. We are going to look into the concept of vector embeddings, which is a core of what semantic search is based upon. And then we're going to drill down a bit in the underlying technology, like vector databases, what they are and how you can work with them in the Wolfram language. And then we can like climb back to semantic search and interacting with the LLM through context augmentation and retrieval-augmented generations. Okay, so without further ado, let's characterize what the main topic of this talk is. Semantic search is basically about retrieving results and documents based on meaning and context around the query and the passages you're searching, not just simple keyword matching. Let's try to look at this a bit more in detail to understand what it means. So here, I put together a small slide where I have a search bar, and I'm doing some simple keyword matching here that I coded. I put the code of this in the notebook. We're gonna see that later. So this is traditional search. Let's start by searching something like let's start typing mount, so it highlights a couple of matches here, or I say Paris, quite easy to find this stuff here. Tower, and I can do more powerful things here. You're gonna see that in detail, but it's very difficult to overcome like the fuzziness of human speech. Like I might say capital of France. And like many people here will know that the capital of France is Paris, and for sure, large language models they know that, they're trained on that, and it's written in a lot of text around the web, so like it's quite easy to pick it up in any decent training. But this is something that is almost impossible to do in traditional search. So let's see how this very same thing will map to, let me scroll down a bit, I hope you can see both. So here I put traditional search and semantic search, and you see that here what I put, this is a bit fuzzier as a concept. So instead of giving a score based on, and here I could have added a score, honestly, just for simplicity, I didn't do it, based on matching keywords. But here I'm just putting distance, and in a minute I'll explain what is this distance. But you can imagine this about how close is each passage in this case. Could be longer sentences, like paragraphs, or like some tables if you want, or images or other things. But in this case, I have these small sentences, and I want to know how close they are to my query. So the input text here is typically called query in search term, and you can see that the Eiffel Tower is located in Paris is actually the first one. So I can still match like more regular things, but I can write something like tall landmark maybe in France, and you see, I mean, this stuff is adapting to what I write, and just tall landmark probably was close to a mountain, but adding some more context like France help disambiguate. Even in France is not appearing here in the indexed material. Yeah, so this is the core idea behind it. Like I want to retrieve things by doing fuzzy matching, like semantic matching, let's say, is even better. Semantic matching against my query. Okay, let's see a bit how this thing can happen. So the core of semantic search is vector embeddings. So embeddings are numerical representation of things, in general, things. It could be them images, it could be for single words. In this case, what we are going to embed compute like in vector space is whole pieces of text, like small sentences. And here, for example, I added our 3 documents from before, Mount Everest, Wolfram Language, Eiffel Tower, and then add some sample queries so we can see how they would fare in this embedding space. So what's the capital of France, toll, and write code. Now, if we take these embeddings and we use something like dimensionality reduction to plot them in 2D, we can see something like this. For example, this is completely arbitrary, but gives an idea. I mean, this is real dimensionality reduced embeddings, but the full picture is always more complex, unfortunately. So we see that toll ended up pretty close to Mount Everest, not so far from Eiffel Tower, but yeah, I mean, distances here are not really Euclidean, so let's not stress over it. But close. I mean, the closest thing is still a good measure here. Eiffel Tower is close to the capital of France, and the Wolfram language is a great programming language, is close to write code. So basically, we can see that without having any form of direct match in the strings, we were able to kind of end up in the ballpark of the relevant things. Of course, in a real world scenario, you will have a lot more documents with more complicated paragraphs, and like the context is going to be a bit more complicated. You might ask, like a famous computer company with Apple logo. I guess Apple is also in the name of the company, but you get my point here. You can use periphrases. You might be unsure about certain things. It might be that you are storing things with some technical name, and you use a more generic name. There's synonyms, and there's all sorts of things that in traditional search you want to take care of manually. But here is taken care of by this semantic representation through vectors. And I have to add, this whole thing has gotten a great boost with large language models. So before this talk in the conference, and been a lot of other talks, there was my colleague Timothée talking about the state of the LLM in the Wolfram language. I mean, LLM are very powerful. One thing you can do is you can kind of peek inside the model of reasoning, the thinking, let's say, or the processing, if you want to be more prosaic and down to earth. And of course, I mean, those are neural networks in the end, and they work on tensors. They do arithmetic operation on tensors. And so the task of predicting tokens like next words and giving you sentences and giving you entire things that they can write thoughts, they can write tables. I mean, all of that is done through some representation of the inner word, some representation of the context of what you're asking or what state of the knowledge they have is. And those are vectors, and you can basically piggyback on that and extract those vectors, and you can even slightly fine-tune, like retrain by adjusting a bit those models to be more optimized in creating those vectors if you don't care really about text generation. But the basic idea is that you train these models for a task like text generation, and then you piggyback on that knowledge to extract vector representation. This is very typical for neural networks. It has been done since a decade at this point, using convolutional networks, for example, to extract image features. You use a built-in representation that the network has created during the training, and then you use that to represent the object. So you let the network process your object, and you extract this vector representation. These numbers are practically meaningless at this point. There were some experiments, I remember, like in monkey brains, try to understand how the activation function, how the firing of each neuron in the brain, when they would see faces, would correlate with specific elements of faces. Was a paper, I think, called Eigenfaces or something like that. So by tuning individual elements, you could adjust, I don't know, the elongation of the mouth or something like that. These stuff, I mean, maybe they do have a very, very abstract meaning, but is like so many stores, like so many, like the pyramid is so high at this point, and you're looking at the top, that the connection to the bottom is too far to see. So I'm sure there are a lot of people that would like to like win some Nobel at this point. It's legit by publishing some explanation of what embeddings practically means, but I'm not aware of any. So right now we are just basically blindly using them as a representation of objects. And so I'm answering this live because people are asking how these are calculated. You run these things through a neural network, and there are several ways to do that. You can use APIs. You can connect, for example, to the OpenAI API or Anthropic API, Google API, and ask for vector embeddings, or you can run local neural networks that do that. So of course, as is typically the case, big models that are run elsewhere, they know more things. It's like to ask like a professor about, tell me what you think about what is correct to this sentence, or you could ask like a child. You will have your answer locally and very fast, but you will have lot less extra information around it. Okay, let's move a bit, and I'm going to address some questions when I reach the relevant slides, and then at the end we're going to have time for Q&A. Okay, so how is this type of storing vectors different from traditional search databases? Okay, let's say how we would do this for normal search things. Like typically what you do is you just create something like a table format. You will have your like SQL or whatnot. You will have an ID. You have your document, and like arbitrary metadata. You might add some dates about when this was generated, the author. I think there's some horizontal scrolling. I added use a repository function random pet name to add the author. So like probably Molly did this one, and some like I don't know. I'm not good with English pet names. This is why I use the function. So I mean, the idea is that you create these rows, and then you might also do some pre-processing, like add keywords already that might go with the documents. You can imagine that these things stands for like a I don't know, a PDF or like a report, customer emails. Like it can be like really as varied as the word, the amount of stuff that you can store this way. But the core concept is that you put stuff in, and then search is performed by matching like literal queries against what's in the index. And there are tricks. I mean, I don't want to discount traditional search, because there are bags or a bag of tricks that you can use to improve results, like tokenization. You can remove stop words. You can do stemming and lemmatization, like reduce words in normal form, add synonyms, perform fuzzy matching. So even if you like misspell some letters, or like directly do spell correction, you can expand the query with synonyms. Okay, here I put some ideas. Like I'm asking, like, what is the highest mountain that this is misspelled intentionally in the word? Then you could run some spell correction, so we get the highest mountain. We can do tokenization. So this is the string, so we could split this in arbitrary pieces, but we split these in tokens that have a meaning, like English words, for example. This is like tokenization for LLMs. Simply LLMs have different purpose for splitting stuff, so it doesn't have to be one-to-one with what we have in our natural language meaning. So here, for example, of course, like this sentence is very unlikely that I can find this in my document storage, but I can start by matching individual words. I can remove the stop words, so I end up with highest mountain reward. Then I can do something like stemming and lemmatization. For example, here, like highest becomes high, and I add higher, and I add highest. I can do query expansion, like adding synonyms. So here I'm adding peak, and word goes also to earth. So this stuff will allow basically, and then at the end I can also use inject some logical keywords like and, or like for example here I was talking about Apple computer before. You could do Apple and computer, or Apple not fruit. Apple or orange probably goes more in the fruit direction, but Apple not fruit and Apple and computer will help constrain results to document that not contain hopefully the report, the weather report on the Apple fields for this year, but more like the financial reports for Apple, the company. So at the end, you do all of these. So for example, like tallest mountain on Earth would, if you go back, so sorry, I have to scroll a bit because I don't remember what I have for documents. Yeah, here, Mount Everest is the highest mountain in the world. So like tallest mountain on Earth, or like tallest peak on Earth will match this query eventually. Yeah, but you can see how this can quickly spiral out of control. Like I'd say, like the Eiffel Tower is located in Paris, and I'm asking what is a tall landmark in the capital of France. Where do I stop? If I have infinite space, I can expand Paris to also contain capital of France. But the reverse is not so easy. For example, if I say capital of France, it's not so obvious that how could I identify that piece and convert it to Paris programmatically? I mean, knowing in advance how to do that. You have to hard code. Basically, you have to hard code a lot of things. While neural networks are more naturally geared towards dealing with this fuzziness. Yeah. And this is why this whole representation system allows for a better better match. Oh yeah, sorry, here. Now let's see how we do the same thing in vector databases. So in vector databases, you take your sentences, you embed them in vectors, and then you typically do something useful, like instead of storing those vectors in lists and just try to force against like brute force match against that list, you use some form of like sort of KD trees, but more approximate to store them in an efficient way, in a format is efficient for querying. Yeah? What you care about is like you do all the offload, all the processing offline to building these databases, and then you want to be very fast. So when you search, you encode your query, and then you do a vector search, which is typically an approximate vector search, yeah, because you're not interested, as in many situations with neural networks, you're not interested in the absolute global minimum, yeah. But I mean, if you return the first 3 results, it doesn't really matter if the number 2 is actually the closest. Yeah, if they're both talking about high mountains and you are asking about high mountains, you're fine. Yeah. Especially given that these numbers are not particularly meaningful. Yeah, so like making small errors shouldn't affect the result much. Okay. So I already mentioned what are the key capabilities of these. Like you want to efficiently search in high-dimensional space. You want them to be scalable and optimized for large data set. Imagine that you might want to embed your whole knowledge base of a large company, like all support articles, all the history of conversation with the customer, or like you can think about that. And then you might want to update them very quickly. So it's typically very difficult to remove things because you have this large growing structure, and it tends to be easier to rebuild from scratch if you want to physically remove nodes. Tend to just mark nodes for deletion, but you never really touch the whole thing. But it should be easy to add, so you can add new documents. Now, I talk a lot, I showed a little code, so how can you work with vector databases in the Wolfram language? It's quite easy. Well, here I'm just using this to delete all my previous instances. I can create a vector database with the obvious function, create vector database, and here I'm giving it a name, but you don't have to. Like an ID would be auto-generated if you don't. You can create an empty one, or you can start by adding some vectors at the beginning. It doesn't really matter. The important thing is that you can grow the database. For example, here I'm adding these 3-dimensional vectors, and then you can search the database. This is like nearest, basically. So if I say 111, it returns this one. If I say 11,2, it gives me the first 2. And there are a few things that you can customize right now. You can add working precision. like fully supported. There's RIA64, which I don't recommend. You can go down to RIA32, which is typically better, integer 8. And very experimentally, just mentioned here, there's also float 16 that works. So you can save up a lot of space in the database by encoding in float 16 compared to float 64. Then you can do a few things, like you can, we are using this generated asset location option from video. So you can use it when you create the database initially to specify what it is, give a directory. You can use the head as a constructor to create it in the new location. So you can move things around, like in the cloud. Then, like a few conveniences, even in the first version, you can add feature extractors that generate. You can only use the one that generates constant length features, like not sequences extractor. But for example, like image features is a nice way to encode images using neural networks. So I don't know if you can see these images. There are 3 squirrels and 3 monkeys. So I'm just creating a vector database with those using a feature extractor, and now I can directly query with images because the feature extractor will be applied to the input. Okay, so let's see. So some people are asking, no, we did not create our own vector database. We are using right now. We're using the usearch library, which is a very efficient one. Okay, we have several questions. I'm going to take them here because we're already talking about databases. No, if you search, like people are asking, you search with high dimensional space, you must do dimensionality reduction. Well, no, the whole point is that this system is particularly efficient to work in high dimensional spaces. So you don't need, you can reduce the vector dimensionality. I don't know, if you have like a 1,000 dimensional vectors, then it's quite, maybe you have only few elements, so you can use, I don't know, 100 dimension, 500 dimensions. But in full generality, there's no reason to reduce the size except for like storage space, because this stuff is extremely efficient to work in high dimensional space. Searching for matrices and tensors compared to just 1D vectors is not as optimized. So you can use nearest for that. That will work, possibly the custom nearest function. But the whole out-of-core, highly optimized pipeline is mainly for vectors. And few more things. People are asking if you can look at the 2D plot of the embeddings to infer clustering in the semantic space. You can definitely do. It's as every like visual method, it's limited to what you can see. You can do 2D, 3D plots, but not much more. So embedding text queries, on the other hand, allows you to search in the high dimensional space. Okay, before we looked at the questions, let's see a bit. I promised to talk about semantic search, so let's see a bit the other hand of the whole problem here. Like, how do we put back like vector databases into a text search like interface? So to do that, we added new functions also on the text side. You have create semantic search index, which mirror creates search index. So for example, here I'm creating one using Alice in Wonderland as a default, like available default text. And then, for example, here I'm doing a sport game as a semantic search on this index, a sport game as a query, and saying, give me the first 3 items. The rest is just formatting. So here you see we get something here. She boxed the queen ears, people running, croquet balls, flamingos. I don't remember this part. I read the book so much time ago. Oh, the game begun. Yeah, this is something about games here. Exactly. Then here we have, they were playing, players, croquet ground is probably the same match, but this is another piece talking about sport. And here there's a race course, Dodo. What is party? Yes, running a race course. So here you see, there's not even sport here. Probably there's definitely not game, but the generic idea is that you're talking about a sport game. And so this is the type of thing that you can do with this system. You can just put in the meaning and trying to find matches by meaning. And similar to vector databases, you can of course grow these indices. So I have update semantic search index, and I'm adding, for example, I don't know, it's called Alice. So I was adding Alice in Wonderland Wikipedia page. So I can do this, and I can query things using this page. Now I promise you to show, like, this is very simple, like the stuff I created at the beginning. This is creating an input field where you can use to type stuff, and then here I can just create semantic search index, what I just showed on this list of strings, and then use semantic search on the index with my query, and I'm specifying properties here like item and distance. So now you can understand that what this distance is. Yeah, this is the vector distance between the vector embedding of the indexed elements and the vector embedding of the query. And if I type here, like tall, mountain, you see stuff is changing, the distance is changing. Now, one thing that my colleague Timothy has shown already is that you can use the new function here. We have this function new in 14.1, which is called LM prompt generator, and you can use to do contextual augmentation. So here, for example, I'm creating a function that's called LM prompt generator because I can use it to create prompts for LLMs, and is adding the username, the date, and the place. Yeah, and I can put it in my prompt list, and I say I always greet the person you're talking to, add contextual information in a seamless way. I mean, whatever you want to, you can optimize these things to do exactly what you want, or like hopefully do exactly what you want. And then this one here says, hello, Giulio. I think I'm on VPN, so it's saying, how are you doing in Champagne? Spoiler, I'm actually in Rome, but the machine doesn't need to know. You can run arbitrary code on the prompt. Like here, I'm doing string length to pass the length of my input, and I'm saying, oh, check that the input has at least 100 character long. Then you don't have to rely on the LLM either understanding this or being able to make a tool call where you, like, the LLM is asking you to run the function for it, but you can directly provide the information. So yes, I write the sky is blue, and the LLM is sorry, but no, he knows exactly how this is long, and you can tell, no, this is shorter than 100. Now, final merging things together. We have optimized LM prompt generator to work with semantic search indices. Yeah, so you can, for example, here you can. I'm not going to download this because I don't have it yet, and it's quite large. It is a semantic index of the whole documentation, and you can put it back in your LLM pipeline with stuff like CodeWriter, for example, and which is asking the LLM to answer only with Wolfram language code. This is similar to what the chat notebooks interface is using. And I'm asking create a new document with a plot of the sin function, and this is giving me, maybe I don't know nothing about front-end code to generate directly notebooks from other notebooks. So this is telling me I could use document notebook with a text cell and an expression cell, and actually it generates that. So this is the title is here is just the presenter style is making it white on white, but if I don't go full screen, you'll see that. So basically, this is a full circle. Yeah, you index your information, in this case the whole documentation. Then you ask some stuff, and you use a semantic search to retrieve the relevant bits, and you use a language model to read your question and the relevant bits. So you use twice your query, once to find the relevant bits of the information, and the second time you pass it to the LLM together with the relevant information, and then it can give you much more accurate answers, but also up-to-date answers, because you can use, you can update the database live and provide recent information. So yeah, basically this is the gist of it. I'm adding here some extra resources that you can check, and thank you. And now I'm gonna take some more questions maybe. So let's scroll to the top. Okay, if the vector search doesn't seek a global minimum, this means you still can't use it in the same way as traditional search. Well, the point is, what is the correct answer? Yeah, we are entering the realm of semantic similarity, which is quite arbitrary, because you could ask two people to rank the content of a database based on similarities with the query, and they could come up with two different but equally valid rankings. But even traditional search, it's only as good as those optimizations that you can put in. So you get a true absolute minimum of like some metric, but then you're just moving the burden to the definition of the metric. So here the burden is mostly on the training of the embedding model. Again, in practical cases, is not really a problem that you're doing fuzzy matching, at least from what I've seen. Portions of that you can upload to the cloud, and portions of the process that you can do locally. I mean, in principle, you can do everything in the cloud. I mean, definitely you should do on some powerful machine. You should create a database on a powerful machine if you have a lot of documents, of course. Or you can use an API. You can use a company API if you have some sort of enterprise access to LLMs to generate those embeddings. And that is something that you do once. The big thing you do once, and then you can do it incrementally and add new embeddings as new documents come in. Now, what needs to happen locally is basically, for the search part, you just need to encode the query. So that is a tricky bit, because you need to encode the query with the same system you use to encode the whole database. Yeah, so if you use OpenAI embeddings to encode the database, you need to use OpenAI embedding to encode the query, because they need to be mapped to the same space. So that will put a constraint on the infrastructure. But once that is set, then what happens locally is something very small, like encoding your query, for example. But you can just directly send the query as text to a server, do the matching there, and then the server will answer with the relevant documents. So you don't need anything locally, actually. If you have small vectors or small local models, you can. I mean, here I'm doing stuff locally because I'm using a small model. If you're not doing dimensional reduction, okay, people are asking about how can you store high dimensional data? You can just flatten them. That's one way to do that. I mean, this is the topic of feature extraction. How do you reduce a matrix or a tensor to a vector? Yeah, one way is definitely to flatten it. When people are asking me about high dimension before, I was thinking more about long vectors, but this is like high rank tensors. So yeah, you need some form of 1D representation to store stuff in a database like this. Okay, let's try another question. Okay, how is the size of text returned for a hit controlled? So I didn't drill down into details, but you have method options where you can specify how the chunking is performed. Yeah, here's one of the main points of semantic search compared to plain storing of vectors is how do you split text in smaller chunks. Yeah? So let me tell you that the best way is to do it manually, always, because you know what the context is. For example, you might want to add a title of a paper of a report to every chunk, and then you might want not to split tables, or you might want to split tables in a meaningful way. So it's there's one way of chunking for each document almost. What we do natively is geared towards text. So the default splitter is trying to split the text by paragraphs using double new lines, tabs, and stuff like that. If it doesn't manage, it will split using new lines, and if it doesn't manage, it will split using words like spaces and word boundaries. So at the lowest possible level, you split into words, and then you just aggregate words to reach a certain size that you can control by option. You have a minimum and a maximum chunk length that you can specify by option. But this stuff for text works pretty well. If you want, like for example, for the documentation, We have done manual splitting because we wanted to be a bit more in control. There was code in there, so it's almost impossible to have an automated function optimized for every use case. Okay, is it training a neural network or an LM necessary to obtain embeddings suitable for semantic search? Well, it's not necessary. You could use, as it's specified here in the question, some word vocabulary and embedding layer. The problem is, first, it's difficult to go from word embedding to sentence embedding. That was a really open problem. As far as I'm concerned, there were no solutions that was completely acceptable before LLMs. The big advantage of LLMs is that we'll eat the whole sentence, process the sentence. Attention mechanism is looking at the whole sentence at once at the end, and give you a vector representation for the whole sentence. So this is unparalleled compared to even more classical neural network techniques. But in practice, my example with image retrieval was using a standard convolutional network to create vectors and storing the vector in there. So that's completely, you can use vector summing from other places. It's just that the type of usage with the text queries works particularly well with LLMs that are trained on text generation. And they tend to know, the other point is context. They tend to know a lot of context, especially large models. They have a lot of context built in. Which small vocabulary models they don't have. Okay, let's try to do another question. List of proper names and database items. Okay, so do you ever use a list of proper names as database items? I mean, you can store whatever you want in the database, but if you want just to retrieve a name from a list of names, and you don't think about convoluted queries like company headquartered in Champaign in Trade Center Drive, instead of saying Wolfram, it's probably better that you just do direct matching. What you can do is you can say, and you can also do in the language using tags. You can tag like items, like chunks, paragraphs relevant to a specific company, and then use that as a return type. So when I'm, you can customize all of these, but when I'm asking something like this, I get Wolfram because I have the address of Wolfram. And when I ask, the company led by Stephen Wolfram, or by a famous Stephen or something like that, I also get Wolfram because there's information about that in the database. I don't know if I got this completely right. But let's try to go ahead because I know there's another talk now. In the Alice in Wonderland case, how the text divided into the pieces, I think we already answered that about the chunking. Is automatically split using new lines. What else do we have? I think we look at most of the questions. Oh, there was one that I think I answered in the presentation. Why doesn't the retrieval part of retrieval-augmented generation suffer from lack of matching synonyms? Simply because it doesn't do direct matching. It matches on vectors. Okay, I think everything is answered. Well, thank you, and I encourage you to go to our machine learning talks and the rest of the talks. And we have some office hours with machine learning team tonight or today, depending on where you are in the world. So come if you have more questions. Thank you.